Bismillahirrahmanirrahim. Dear students, Assalamu alaikum. This second video lecture is the continuation of my previous first video lecture of week 7th for the course Applied Mathematics 2. Dear students, in the previous first video lecture we have learned about the solution of first order linear differential equations, and now today in this second video lecture we are going to learn about the solution of Bernoulli differential equations. I have already told you that there are some important forms of methods through which we can know the form of equations and then use or apply the method which is required for the solutions of first order differential equations. So first of all, here today I want to tell you again about the classification of first order differential equations. And dear students, you know that we have learned about all these classes, that separable differential equations and its solution, homogeneous differential equation and its solution, exact differential equation and its solution, linear differential equation of first order and its solution. Now the fifth form is Bernoulli equations. But for this Bernoulli equations, I want to tell you today again about the procedure of all these classes. Then we will come to discuss the Bernoulli equations and its solution. So separable equations mean separable variable. The solutions procedure of first order separable differential equation is that a separable first order differential equation has the form dy by dx is equal to g of x divided by h of y. So for the separation of variable, try to join the y function to the operator dy and the x functional terms to the operator dx. To join this h function, because h is the function of y, to join h function with the operator dy, and to join g function with the operator dx, and the operator dy and dx will not be in the denominator form. So rewrite the equation as h of y dy is equal to h of x dx. So this is the separable form. Now after separation of variable, taking integration on both sides, you will get the solution of this differential equation. And the solution for y, and if there is initial condition given, then since we have a constant of integration in the solution, then use that initial condition to find the value of that constant term, which is called c. C is the constant of integration. Now homogeneous equations. The condition of homogeneous function is f of lambda x comma lambda y is equal to lambda power n f of xy. So if a function f of lambda x comma lambda y can be written as lambda power n f of xy, then the function will be homogeneous, where this n represent the degree of the homogeneous function. And so since we have first order linear differential equation like m is a function of xy dx plus n is a function of x and y dy is equal to 0. If the function m and function n are homogeneous, then this differential equation will be a homogeneous differential equation. And for the solution of homogeneous equation, we substitute, first of all we write the function in the form of y by x, then substitute y by x is equal to v, then y is equal to vx, and dy is equal to x dv plus v dx. It's mean that dy by dx is equal to v plus x dv by dx. After using these substitutions, putting these terms, we obtain a new differential equations in the variable v and x, and that equation will be easily separable for the variables, and then we can solve by taking the integration. Now, exact differential equations. Dear students, suppose we have first order linear differential equation m dx plus n dy is equal to 0. Then this differential equation will be exact if partial m by partial y is equal to partial n by partial x. So first of all, check whether this differential equation is exact. If this condition hold, partial m by partial y equal to partial n by partial x, then the given differential equation will be exact, and then we can solve easily the given differential equation by taking integration of the m function with respect to x and plus integration of n terms with respect to y, but their term of n function which not containing x is equal to c. And if partial m by partial y does not equal to partial n by partial x, then the given differential equation will be not an exact differential equation. So if the differential equation not exact, then we convert the non-exact differential equation into the exact form by multiplying an integral factor and then solve by this formula. So dear students, note that if an equation is non-exact, then try to convert that non-exact differential equation into the exact form by multiplying an integral factor. So first of all, find an integral factor, then multiplying that integral factor to the non-exact differential equation, the non-exact differential equation will become an exact differential equation. But how to find an integral factor, we have already discussed 4 cases for finding an integral factor in the previous lectures. Now the 4th case is a first order linear differential equations. A differential equation of the first order m dx plus n dy is equal to 0 will be a linear if these 3 conditions are satisfied. The dependent variable, say y, and its derivative occurs in the first degree only. The dependent variable y and its derivative occurs in the first degree only. The second condition is that the product of y and its derivative are absent. Since in this differential equation the dependent variable is y, so the dependent variable y and its derivative occurs in the first degree only, the product of y and its derivative are absent, and no transcendental function of y and its derivative are present in the given differential equation. So if a differential equation is a linear, then the general form, the standard form of a linear differential equation of first order will be dy by dx plus p of x, p is a function of x, into y is equal to q is a function of x. So if a differential equation is in this form, then easily we can define that the given differential equation is a linear differential equation of first order. So first of all, find integral factor. So to find the integral factor, the formula for the integral factor is e power integration of p function with respect to x, and then multiplying that integral factor to the given differential equation. The given differential equation will be an exact equation, and easily we can find the solution of a linear differential equation after finding the integral factor by using this formula. Integral factor, suppose the integral factor represented by mu, integral factor multiplied dependent variable is equal to integration of the product of integral factor and the q function with respect to x plus c. Now Bernoulli equation. The standard form, the general form of first order Bernoulli equation is dy by dx plus p of x into y is equal to q of x y power n. So dear students, note that this power y power n depend equation depend on the value of n. If we put this n is equal to 0, then this Bernoulli equation will be a linear equation. Since we have already discussed for the linear equation that the degree of the dependent variable will be 1, like in the previous slide, that the dependent variable y and its derivative occur in the first degree only. So if we put in this equation n is equal to 0, then the degree of the dependent variable and its derivative is 1. So the Bernoulli equation become a linear differential equation. And if we put n is equal to 1, then Bernoulli equation will be separable equation form. We can easily solve the Bernoulli equation by separation of variable f n is equal to 1. But if n is greater than 1, then how to solve the Bernoulli equation? Let's to discuss the procedure for the Bernoulli equations f n greater than 1. Divide Bernoulli equation over y power n. So we get 1 over y power n dy by dx plus p of x y 1 minus n is equal to q of x, and put the suppositions z is equal to y power 1 minus n, then taking the derivative of z with respect to y with respect to x, dz by dx is equal to 1 minus n y power minus n dy by dx, and find the value of dy by dx from this expressions, and putting in this equation we obtain 1 over 1 minus n dz by x dx plus p of x y power 1 minus n is equal to q of x. Now multiplying both sides by 1 minus n and putting y power n minus 1 is equal to z, we have a new differential equation dz by dx plus 1 minus n into p of x into z is equal to 1 minus n q of x. So dear students, using some substitutions we can transform the Bernoulli equation into a linear form, and then we can solve this equation easily by this formula: integral factor multiplied dependent variable is equal to integration of integral factor multiplied q function with respect to x plus c, integration of the product of integral factor and q function. So dear students, here note that after using this substitutions we have a new differential equation which is clearly a linear differential equation, and z and x, dz by dx, z is the dependent variable. So first of all find the integral factor. Since z is the dependent variable, so p is the function of x, so find the integral factor, and then using the formula integral factor multiplied dependent variable is equal to integration of the product of integral factor and q function. So here 1 minus q of x, this full term is the q, represent the q function, and 1 minus n into p of x represent the p function, and z is the dependent variable. So let's move on example. Y dy by dx plus y square divided by x is equal to 3 sine of x y power minus 2. So this is a Bernoulli equation. For the solution, dividing both sides by y, we obtain dy by dx plus y by x is equal to sine x into y power minus 1. Now using some substitution, for example z is equal to y square, and then taking the derivative we have dz by dx. Taking the derivative of this supposition with respect to x, dz by dx is equal to, using the power rule, 2y into dy by dx. Find the value of dy by dx from this expression, and then putting in this equation we have dz by dx plus 2 into z by x is equal to 6 sine x, and this is the linear equation, and z and variable x. Z is the dependent variable and x is a independent variable. So this equation is linear and dependent variable z. So first of all, find the integral factor. The integral factor formula, u is equal to exponential power integration of p with respect to x. Here the p function is 2 by x. So the integration of 2 by x is 2 log x, and we can write exponential log x square. So after simplification we get the integral factor is a x square. Now using the formula for the solution of this linear differential equation, so the integral factor multiplied dependent variable. So here the dependent variable is z is equal to 6 sine x is the q function. So integration of the product of integral factor and the q function. Q function is 6 sine x. Now 6 is a constant term, so taking the integration of x square and sine x with respect to x by using integration by parts, we get 6 into minus x square cos x plus 2x sine x plus 2 cos x plus c. So dear students, for a Bernoulli equation, use a suitable substitutions to convert the Bernoulli equation into the linear form, and then solve by using the procedure, by using the formula for a linear equations. Since the solutions formula for a linear equation is a integral factor multiplied dependent variable is equal to integration of the product of integral factor and q functions. So when we use some suitable substitutions, the Bernoulli equations will be converted into a linear differential equation, a new dependent variable. So in this example we have a new dependent variable z. So this differential equation is now a linear equation in z. So for in the formula, using this dependent variable, that integral factor multiplied dependent variable is equal to integration of the product of integral factor and q function. Q function will be in x, since x is independent variable. So the function of x here in this left hand side, the second term in this in the left hand side, the second term denote the p function, and so in this example 2 by x is the p function. So if we compare this differential equation into the standard form of linear equation, this is a linear equation. So p into dependent variable. So into dependent variable mean this z is the 2x into z. Z is a dependent variable, so 2 by x into z. 2 by x is p function, and at the right hand side the function of x will be the q function. So for the solution of this differential equation using this simple formula, integral factor multiplied dependent variable is equal to integration of the product of integral factor and q function with respect to x plus c. Now let's move in another example. dy by dx plus y is equal to x e power 2x y cube. So first of all, divide this equation by y power 3. We obtain y power minus 3 dy by dx plus y power minus 2 is equal to x e power 2x. Now using this suitable substitutions to convert this differential equation into a linear form. So y power minus 2 is equal to v then minus 2 y power minus 3, taking the derivative with respect to x. So using power rule, minus 2 y power minus 3, again derivative of the base dy by dx is equal to dv by dx. To find the value of y power minus 3 dy by dx, since in left hand side we have y power 3 dy by dx, so the value of y power 3 dy by dx is equal to minus 1 over 2 dv by dx. So putting the value of y power minus 3 dy by dx is equal to minus 1 over 2 dv by dx, and this equation we obtain minus 1 over 2 dv by dx plus the value of y power minus 2 is v is equal to, this is the right hand side, x e power 2x. Now multiplying this equation by minus 2 to convert this differential equation into the standard form of linear equation, we have dv by dx minus 2v is equal to minus 2x e power 2x. Now this equation is linear and in the dependent variable v and independent variable x. So first of all, find the integral factor. Integral factor e power integration of p function. Now since v is the dependent variable, so the coefficient of v will be the p function. So the p function is now minus 2. Integration of minus 2 is minus 2x. So the integral factor is e power minus 2x. Now find the solution of this new differential equation, which is equal to integral factor multiplied dependent variable is equal to integration of the product of integral factor and q function. In this equation, at the right hand side we have minus 2x e power 2x. This is the q function. So integral factor dot q. So e power minus 2x and e power 2x, since the base is same, adding the power e power minus 2x plus 2x 0, e power 0 is equal to 1. So we have integration of minus 2x dx, and the integration of x is x square divided by 2. So 2 to cancel, we have minus x square plus c. So the solution is e power minus 2x into v is equal to minus x square plus c. Now replacing this v by this supposition y power minus 2. So we have the solution e power minus 2x y power minus 2 is equal to minus x square plus c. So dear students, note that for the solution of a Bernoulli equations, in a Bernoulli equation, first of all divide the equation by this dependent variable terms. So after this division, then use a suitable substitution to convert this differential equation into a linear differential equation. In the linear differential equation, we have a new dependent variable for y, since in the given differential equation then the dependent variable is y, but when we use the supposition, for example, y power minus 2 is equal to v, or we use y power minus 2 is equal to z, then in the new differential equation the dependent variable will be z. So since in this example we have the y power minus 2 is equal to v, so v will be the new dependent variable in the new linear differential equation, in the new equations. So first of all, divide the given differential equation by this dependent variable term. We have a new differential equations, and then use suitable substitutions to convert this new differential equation into a linear equation. But in the linear equation, the dependent variable will be v if we use for the supposition v, y power minus 2 is equal to v. Then in the new differential equation, which will be linear, in that linear equation we have a new dependent variable. So when convert this equation into the linear form, then first of all find the integral factor, but But before finding integral factor, first of all convert the new differential equation into the standard form of linear equation. After converting the equation into the standard form, dear students, you will easily get the p function and the q function. So using p function for integral factor and using the q function for the solution. So when you find the integral factor, then using the formula for the solutions, integral factor multiplied dependent variable is equal to integration of the product of integral factor and q function with respect to x. Since the q function will be in x, that's why we integrate the product of integral factor and q function with respect to x. Since the integral factor also is a function of x and the q function also the function of x, so we integrate the product of integral factor and q function with respect to x. And this is the end of this segment. Thank you. Allah Hafiz.